Okay, so it looks like everyone's here. So today we're very happy to have Martin White. Martin has been faculty at Berkeley and LBL for quite a while, and he's been one of the leaders in cosmology since probably the dawn of the modern era of cosmology. I would say started with Toby back in the early 90s. Martin worked on a lot of early interpretation of those results, as well as fleshing out some of the formalism for overall interpretation of CMB cosmology measurements. And since then, he's continued to be very involved in cosmology up through Climb and Beyond, and also through various topics in large-scale structure. But today he's going to be talking about the so-called cosmic brunch and what we can do with higher redshift measurements in cosmology.
Oh, thank you very much. It's great to be back at CITA, although I'm not enjoying the weather. So I want to talk about probing the high redshift universe. This is a bunch of ideas that we've been thinking about for several years now, and I know that high redshift universe is entirely in the eye of the beholder. I mean, what is high redshift to one person is low redshift to another. So what I mean by high redshift for the purposes of this talk is kind of from the epoch of reionization down to the point where we have kind of the peak of the Quasi epoch or the peak of the star formation epoch or something like that. So roughly redshift 6-ish to 2-ish. So if if epoch of reionization is cosmic dawn and the peak of the Quasi epoch is high noon, this is about the best we could come up with for that other period. But if someone has a much, much better idea, I would love to hear it, because cosmic brunch is not inspiring. But this is work I've been doing with a bunch of postdocs and students at Berkeley and elsewhere. So Emmanuel Castorina, who's a postdoc at Berkeley. Chirag Modi, a kind of interesting graduate student. He's graduating this year. He's done a thesis that is half machine learning and half cosmology. I don't quite know how he manages to do, twice as much as everybody else, but he manages to get stuff done. Zvonimir Vlah, who's a postdoc at CERN, and Mike Wilson, who's another one of our postdocs at Berkeley. So let me just quickly give you an outline of where we're going to go so we all know roughly what the scheme is. So I want to briefly motivate why one might think about probing this redshift range 2 to 6. I won't go into tons of detail because I really want to get to sort of the last half of the talk. But this motivation is going to come in two kind of flavors. One will be more theoretical, but the other one will be just thinking about what is coming up down the pike in terms of new instrumentation and where I might expect the observational situation to be changing in the hopes that kind of looking under the lamppost might yield something interesting. And then I'll spend a little bit of time talking about CMB lensing and the selection of high redshift galaxies, because I want to combine those two to talk about some science. And the science I want to talk about is measuring the growth of large-scale structure. So I'll tell you what the promise is, what the opportunity is, and then what some of the problems that have come up as we've thought about how one might go about analyzing such data. And there's basically three problems that come under the name of bias, bias, and bias. And so I'll end with a discussion of future directions. So if we just take a step back and ask, where might there be breakthroughs in cosmology? At some level, this is essentially a mode counting exercise. For most things you want to do, if you want to measure something accurately in cosmology, you typically need to get around sample variance, which means you just need a very large number of modes. Now, formally, that's not literally correct, but practically it does turn out to be the case. So, if I was interested in probing the early universe, inflation models by looking at primordial non-Gaussianity, features in the inflationary spectrum, probing the degree of flatness in the current universe, all of these things that people are claiming might be signatures of beyond vanilla inflation, they all essentially turn into a mode counting exercise. Similarly, if I'm interested in probing the particle content of the universe, for example, neutrino masses or any other light relics, that is essentially a mode counting exercise. If I want to test general relativity, especially if I want to test it on large cosmological scales, again, that's a mode counting exercise. And for all of these, right, with the sort of possible exception of dark energy, in general, things going nonlinear is just not your friend, because when things go nonlinear, you tend to decouple the initial and final conditions. And so if you're after so-called primordial physics, then you want to try and stay in the linear regime. Now, the goal of all of us trying to work through this problem is to maximize the signal to noise of new physics, or if you prefer not necessarily new physics, new insights on the physics that we've got, right? All of these tests or ideas that we're trying to do. And unfortunately, I was not issued a crystal ball which tells me where or even if new physics is going to show up, right? So I have no idea where to look to maximize S. So my approach, for the purposes of this talk, if nothing else, is to try and maximize the signal to noise by getting the noise as low as possible. So where can I make highly precise tests of the existing theory? Because I don't know where it's going to break, but I can forecast where n can get small. And then, I confess that at least half, possibly more than half, of the driver behind this is I'd like a problem which has both well-controlled and interesting theory. While it might be that there are places with very, very low noise that are really boring, I don't want to work on those. And so I'm looking for problems here where the theory is interesting, I think I can do a precise measurement, and there's a chance that I can show up some new theoretical thing. And all of these arguments essentially push me towards going to try to go high redshift, because that gives me more volume, less nonlinearity, and because it has been less well-studied observationally, it's also kind of an area where the theory is still open. So here's an example of many I could have pulled out, but this just shows you a prediction for the amplitude of fluctuation sigma 8, or the growth rate of fluctuation, so the derivative of the growth rate, f sigma 8, from redshifts 5 down to 2. And what I've plotted here are the predictions of lambda CDM, taking the Planck data, using that to set the cosmological parameters of the basic model, and then evolving it down to redshift 5, 4, 3, and 2, showing sort of the 1 sigma error. Yeah?
What's sigma 8?
So sigma 8 is the amplitude of the fluctuations in the universe, right? So some amplitude of the power spectrum, or the square root of the power spectrum. And f sigma 8 is the time derivative of that, right? So this is a measure of how much the fluctuations in the universe are growing, right? The anisotropy in the universe is growing.
So this would be like the dimensionless quantities.
These are dimensionless quantities that are all, slightly less than order 1, right? That's right. Both. So they're in Hubble units, so that everything's scaled out to be dimensionless, right? So between a redshift of 1,000 and the present day, the fluctuations in the universe grow by roughly a factor of 1,000, right? And what's amazing is that the theory, GR, predicts that growth extremely precisely. And in fact, in this region here, we're essentially matter dominated. That means the fluctuations are predicted with incredible precision. And so you can see the error bars here are actually 1.1%, right? They're not independent, right? Because it's the same theory that is predicting it across time. But there's a 1% prediction here for the amplitude of fluctuations that you could go and test. We have not measured the amplitude of these fluctuations at these redshifts at anything approaching 1%, right? It's more than an order of magnitude worse, but there is a 1% level prediction of the theory that in principle you could go and shoot at. And what's interesting about this is if you ask what dominates this error bar, it's not whether or not we believe GR, I think we probably do, but it's actually dominated by things like the neutrino mass uncertainty, right? So you can look at this two ways. One is if I knew things like neutrino masses, I could ask the question, is general relativity right? Does it match this growth to 1% as I expect? The other thing you could do is you could turn around and say, oh, well, I know GR is right. Come on, give me a break. We've measured black holes and all kinds of stuff now. So could I get it at other things like neutrino masses? And I'm throwing neutrino mass in here, but I could mean effective species or other light relics or whatever the particle content is that you'd like. And just to show you sort of this neutrino effect, it's relatively straightforward to derive that the density perturbations in the matter will grow as a certain power of the scale factor during the matter-dominated era. And that power of the scale factor would be 1 if all we had was cold dark matter. But when you have massive neutrinos, it's reduced by 3/5 of the neutrino mass fraction. Right? So over time, the presence of light neutrinos will cause a slight damping, at least on small scales, of the growth of fluctuations, because neutrinos free stream and don't clump. Right? And so this is just a plot from a paper by Byung-Hee Yu and company, where they normalize these fluctuations to 1 at redshift 7, and then show what happens in the absence of neutrinos compared to what happens with neutrinos. We don't care what the boxes mean in this particular case, but what you can see is you get this growth suppression, but it's very, very small. Right? And so the question then is, could you go about measuring these fluctuations over that redshift range? Okay, so that's part 1 of the motivation is I want to look for places where I can do precise tests. Part 2 of the motivation is we're about to turn on several new facilities representing literally billions of dollars worth of public investment and hundreds of person years, right? And I've written, in some sense, the 2 poster children for the particular case I want to talk about today. This is obviously some artist's rendition of LSST, and then this is a version of the CMB stage 4, although it won't be tied to these particular experiments. These are sort of the motivation in the back of my mind. And if you kind of turn that around and ask what's happening on the optical and submillimeter front, in the optical, we have these major new imaging and spectroscopic surveys, right? So just to throw up a smorgasbord of acronyms, right? The Dark Energy Survey and the DCAM Legacy Survey are both now completed. All those data are in the can. For dark energy survey, they've released part of year 1. For the DKM legacy survey, I think all of the data are currently public, so these things are done, right? That's done deal. The dark energy spectroscopic instrument is already starting commissioning. We should be on Sky in September or so. Data will flow come January, right? So that's an absolutely happening thing. Hyper Supreme Cam is already releasing data and is going gangbusters. Prime focus spectrograph is coming down the pike in just a couple of years. LSST should turn on in the next 3 or 4 years. And then, of course, we have space missions, Euclid and WFIRST. And my point is just that all of these facilities can map extremely large fractions of the sky to depths that we now think of as, extraordinarily deep. So just to put some numbers on that, this just shows, the standard optical bands that we're familiar with from, say, Sloan or something, going into the near infrared. And the dark energy survey is getting us to something like 25th magnitude over something like 5K of the sky, so 1/8 of the sky, more or less. Decals is about a magnitude and a bit shallower than that, but over, I guess, 1/3 of the sky or so. LSST will take us into an era where we're deeper than these over the same area as we get with decals, right? So this is going to be very large area, but still fairly deep imaging, right? So this is obviously not as deep as anyone has ever imaged the sky, but it'll be a huge step forward compared to, 22.5, right, or something like that. So wide area surveys are going to go very, very deep. At the same time as that, a similar revolution is happening at the longer wavelengths with the CMB, where if you take Planck, which is, I guess, currently the largest public data set, the map RMS in kind of CMB persons units is about 30 microkelvin per archiminute pixel over roughly half of the sky that you can use where there's no galaxy, right? Already being built and commissioning is the Simons Observatory, which you can see is 5 times lower noise per pixel, as well as being 7 times higher angular resolution simultaneously, right? So this is a massive advance. And the reason is that we can essentially make CMB detectors now the same way, you put transistors on a chip or something, right? So these things are just going to massive multiplex. Planck had 72 detectors. Things like CMB-S4 will have 500,000, right? It's a huge step forward. And so then, the plan is to build a CMB stage 4, which will be, even another factor of 5 times lower noise on sort of a roughly comparable angular resolution. And these things are covering a gain of order half of the sky. So we're going to have a massive increase in our ability to measure CMB fluctuations. And a very natural byproduct of these next generation CMB experiments, which are primarily funded to look for primordial gravity waves, but the interest that I have, and the one thing I want to focus on in this talk, is high fidelity lensing maps, because this is going to be a real science opportunity, I think. So let me quickly remind you of what lensing of the CMB is. So all of the anisotropies that we see in the cosmic microwave background, those photons come to us from a redshift 1000. They, of course, traverse the entire observable universe to get to us, right? And general relativity is making very precise predictions for how those tiny anisotropies that we see at redshift 1000 have grown over time to form all of the large-scale structure and galaxies and so on that we see today. And so as soon as I know the constituents, I know the initial conditions from the CMB, that means I have a prediction for all of the gravitational potentials that those photons traverse as they travel from the surface of last scattering to the present day, right? And as they do that, those gravitational potentials bend the paths of light, right? So they lens the cosmic microwave background, and they imprint a characteristic pattern onto the CMB, which I can now use to probe the large-scale structure. So this is extremely interesting because it provides both a consistency check. Do the initial conditions plus the theory predict the lensing that I have seen directly in the CMB? But more importantly, from my point of view, they provide me sensitivity to the low redshift universe, which would otherwise be missing from the cosmic microwave background, which is primarily a redshift 1000 probe. Now, this isn't the only way we get it. I mean, we can also study things like the Sunyaev-Zoldovich effects and scattering and so on, but I'm going to be mostly interested in this gravitational effect. So these lensing-induced deflections of CMB photons are about 2 to 3 arcminutes in size. They're coherent over patches of the sky that are about 2 or 3 degrees, so that's some kind of native resolution of the image in some sense. They arise from structures over a very wide redshift range, and I'll show you the actual probability for lensing in a little while. But they're quite sensitive. They kind of peak in efficiency around redshifts 2 to 3, which is going to be a redshift range that I'm particularly interested in. And all of these numbers come from just simple numerology. You can kind of work these out just from basic facts about cosmology. So redshift 1000, it turns out, in the current cosmology is about 14 gigaparsecs away. And if you look at the measured potential perturbations that we see in the universe, the fluctuations are very close to scale invariant on very large scales. And then the coherence scale for gravitational potential perturbations is around about 300 megaparsecs. And that's very much what is predicted by cold dark matter. This 300 megaparsecs is what sets that peak in the power spectrum that you're normally used to seeing when people plot those kind of plots. So just trivially, if you take 14 gigaparsecs, you divide by the coherence scale of the potentials, you get about 50 lensing events along the line of sight for any photon, right? So these are multiply lensed photons multiply deflected photons in some sense. And that's one of the reasons why CMB lensing is bigger than you might naively have guessed, is that you get this factor of roughly 7 in deflection over what you might have thought. Each deflection event is caused by a potential whose amplitude is RMS about 3 × 10⁻⁵. So you take twice that, right, to get the deflection angle. So each one of these deflection angles is about 10⁻⁴, which you can quickly work out. 7 × 10⁻⁴ is about 2 arc minutes, right? So that's where that number comes from. And then halfway to the surface of last scattering is 7 gigaparsecs away. And so 300 divided by 7,000 gives you your coherence scale of around about 2 degrees, right? So these numbers are almost just basic numerology about how the CMB and lensing work. But how do I measure the large-scale structure? By looking at lensing. And the basic idea is just that CMB fluctuations have a characteristic scale, right? That whole series of acoustic peaks in the CMB power spectrum. So if I imagine that truly there was a CMB fluctuation of this wavelength on the surface of last scattering, but it passed through a region of the universe that was overdense, then in this highly exaggerated diagram, these photons are bent by lensing of this overdense region and come down. So I think these photons come from here and here on the sky, where they actually come from there and there. And so I take this wavelength and I stretch it out, and I think it's actually that wavelength, here obviously extremely exaggerated. And so what you do when you do lensing reconstruction is you measure a kind of local power spectrum, and you ask, has that power spectrum been pushed to low L or high L? And then you do that at different patches of the sky. And then by reading whether these things have been shifted to larger or smaller regions, I have magnified, or this is an underdense region, I've demagnified that region of the CMB. And so by combining the shearing effect and the magnification effect, you can actually work out what the projected mass is all the way back to the surface of last scattering. Yeah?
You always assume that the lens is smaller than the lens that you prove?
No, this is just for a diagram. We actually go through with the full integration across the path length, and we do the whole spectrum. But this is literally a cartoon. So and I don't just include the magnification. We also include the shearing effect as well. We actually solve for the full lensing potential. So. But this, I think, gives you at least the physics behind what's going on. So this shows you the current largest area map that we have of CMB lensing. It's from the Planck 2018 release. So the color code here is basically essentially it's the projected mass all the way back to the surface of last scattering. This is kind of an amazing image because it covers the whole sky, and it integrates back to redshift 1000, which is essentially the whole history of the universe. So this is a map of all the matter in the universe. It's a relatively useless map of all the matter in the universe because it's on very low resolution and it's projected across the entire distance of the universe. It's still way cool though, right? Because you've got a map of the entire universe. And this gray bit here is because some idiot put us in the middle of a galaxy, which we've had to mask out. But still, you've covered some very, very large fraction of the sky. And I love this map, but it's important to be clear why I like this map. So Planck was not the first experiment to measure lensing, clearly. It was not the first experiment to measure lensing by large-scale structure, and it was not the first experiment to measure lensing of the large-scale by the large-scale structure of the CMB. So you ask, who cares? Why am I interested in this map? Because Planck represents a turning point, and it's an interesting turning point. It's the first experiment that ever measured CMB lensing by large-scale structure over enough sky and with enough signal to noise that it mattered, in the sense that I couldn't have predicted the result better than I measured it just from the theory. At this point, the signal to noise on the measurement had about the same error bar as the theoretical prediction had uncertainty from other things. So at this point, lensing starts mattering when you're doing fits. It starts mattering when you're doing consistency. So I think of Planck kind of as a coming of age for CMB lensing. Prior to that, we had that demonstration phase where life is grand. You've got a 2 sigma measurement, so everyone's excited because it's now real. But with 2 sigma, you can make a 50% error and still be right. So it's all great. So there's like no pressure on the theorists, right? And then Planck means that you now actually have to get things right. And I think this is in some sense a taste of things to come, right? This is only going to get much better. You saw the factors of 20 increase in signal to noise that we're about to get with next generation experiments. So I think a lot of the science that's going to come from these future CMB experiments is, well, the primordial B modes and everything are going to be great, but it's going to be lensing-based science. And so this is a little bit like what COBE was for temperature anisotropies, right? It sort of said this is going to be big, right? But the signal to noise has to drastically increase. But I don't think that the CMB alone is the way to approach this problem. I think most of the science from these future CMB surveys will come from lensing in combination with those optical things that I talked about, and in particular from surveys of galaxies at high redshift. So I want to talk a little bit about how one gets high redshift samples of galaxies. And this is an extremely well-known problem in optical astronomy that's been studied, I don't know, for 20 or 30 years, and an awful lot is known about it. So I'll briefly review some things that maybe some cosmologists are less familiar with. It's this idea of doing so-called dropout selection. And so if you look at star-forming galaxies, especially in the high redshift universe, say around redshift 2, 3, 4, their spectrum looks, I'll show you a real spectrum in a minute, but it looks kind of flattish and then has a big drop, right? Now the flattish bit is just, the temperatures of stars and what the spectrum of stars look like. This drop is just due to absorption by neutral hydrogen, right? That neutral hydrogen could be in the atmospheres of stars. It could be photoelectric absorption. It could be lots of different things. But you get this 912 angstrom Lyman limit due to the absorption of neutral hydrogen, and then any neutral hydrogen along the line of sight. So if I imagine that this is the actual spectrum, and let's imagine that this spectrum is going to be redshifting through these filters as I place sources further and further away from me. Then when this break is all the way off here to the left, I have roughly equal flux in U, G, and R, and so the colors, right, which is just the log of the flux ratio, will be approximately 0, and so I'll be down here at the origin in this color space. As I start redshifting this guy, this break starts cutting out flux in the U, and so I haven't touched G minus R, that's still at 0, but I'm moving G-wards, right, along this color as I go up. At some point, this break starts shifting into G. Now the relative fluxes in U and G will start becoming more equal, so I start going back down again. But I get redder compared to green, and so I start moving to the right. So the typical color track is you go up, and then you kind of come down on a diagonal. It's not quite this easy, but this is roughly what it looks like. And then if I were to plot up the colors of stars and typical other galaxies, they're all going to live down here in this swath. And so what you do is you draw a little box up here to isolate this range there. And so this is known as a color selection box, or a dropout selection box, or a Lyman break galaxy, right? Because I'm looking for this break in the spectrum due to this Lyman alpha limit. So, okay, that's pretty schematic. What do these things actually look like? This shows you some real composite spectra. I've extended them with power laws out here to the right, but these are real actual spectra. They're ordered by equivalent width in the Lyman alpha line, so you go from strong emission to strong absorption, and then they've just been artificially redshifted to higher and higher redshift. And what you can see is that you get this break where the flux drops by a large factor, or here a very, very large factor as you go across that Lyman limit. And so depending on what redshift you're at, this break has shifted into different filters. So this shows the filters U, G, R, I, Z, Y, and then the 3 Euclid bands in the near infrared. And so you can see that they're kind of ideally situated for finding strong flux out here in the redder bands, and then weak flux out here in the bluer bands, from a redshift of about 2 out to a redshift of about 6. Right? And so that's the basic idea. So the cool thing about this is that dropout selection only requires 3 filters. It's obviously extremely efficient, and it's much, much easier to model than trying to figure out what on earth your photo Z code did, which is quite difficult. Because you only require 3 filters, it's very easy for survey planning to get a very large area, right? Because I don't need to have uniform depths and multi-visit matching and all this other stuff. These objects have been extensively studied. If you try and actually do a literature search on this, there's literally thousands of papers on these things. Going back into the 80s, in fact, you can find some of these papers. We know that roughly speaking, what you select when you do this is actively star-forming galaxies, a fairly similar population in terms of its spectral properties over the redshift range 2 and a bit out to redshift 5 or 6. The rest frame UV spectra are dominated by O and B stars, so these are massive stars with hot spectra. And they lie very, very close to the main sequence of star formation, this so-called star forming main sequence people talk about. And the UV luminosity is very closely related to their star formation rate, which is quite closely, because of the star-forming main sequence is basically given by stellar mass. So we know a lot about these galaxies. We know a lot about their spectra, what kind of lines typically show up, all of those other things. We're going to be focused on things that are close to the knee and the stellar mass function, so something like 10 to the 10 to 10 to the 11 solar mass objects forming a, m dot over m star of 0.2 times 1 plus z to the 3 halves, kind of typical star-forming main sequence kind of star formation rates. And these, since I'm at the epoch of redshift 2 or 3, that's where pretty much everything is star forming. These are kind of the majority of galaxies in the universe in some ways, right? I mean, of these masses at least. Okay, so you get a very large number of galaxies. What I'm showing here is just selecting objects based on sort of, redshift 2, redshift 3, redshift 4, and redshift 5 going down here. This shows you the quasar luminosity function for comparison. So quasars, many more bright objects, but far fewer faint objects. And then these lines show you, just taken from the literature, Schechter function fits to dropouts of redshift 2, 3, 4, and 5. And then the triangles and squares show you what happens if you actually go into an image and count the objects in a box. So the reason you have triangles above the squares and above the lines at the bright end is these are interlopers, right, that are at low redshift but just happen to have colors that fell in your color box, right? So they're bright because they're low redshift. Typically, for example, for these G dropouts or these U dropouts, they'll be bright red galaxies at redshift 0.8 or something like that. Quite often what happens is you've mistaken a Balmer break for a Lyman break or some effect like that. But notice that these points start coming together as you go to fainter magnitudes, right? Once I start going faint, there are, mostly what I'm looking at is these galaxies at the right redshift. And then the points drop below the curves here, because the curves, of course, have been completeness corrected, right? Because they're trying to calculate a luminosity function, and these are just the raw counts, right? So this has had no efficiency folded in, and so this is from whatever the observational depth was, or whatever the data was. But you can kind of see that for the U dropouts, the triangles and the squares are basically on top of each other. So redshift 3 U dropouts have almost no contamination. At redshift 4, the contamination, these are relatively bright elliptical galaxies at a redshift of about 1. But once you get down to about 24th or 25th magnitude, that essentially goes away as well. And these samples, you're getting some reasonable fraction of the entire population with perfectly reasonable imaging depths that you could easily do with things like LSST. And just, I didn't really make a deal about it, but notice that the y-axis here, this is 10 to the 4 galaxies per square degree. So these are extraordinarily dense samples on the sky. So if I take those galaxies that have, roughly speaking, known redshifts, redshift 2, 3, 4, 5, as I do these drops, then I can combine them with cosmic microwave background lensing. And so this tries to show you sort of the overlap. This kind of shaded gray band here, this is the probability that a CMB photon will be lensed as a function of its redshift, I mean, appropriately normalized. And so this shows you the CMB lensing kernel, right? This is how much lensing is occurring as a function of redshift. And you can see it's very, very broad, but there is a peak around a redshift of about 2 or 3 or so. And then these lines here show you what happens if you just plot the redshift distribution of a magnitude-limited sample, right? So mostly focused to lower redshift, and these just show you some kind of characteristic depths. So this is the depth of the sort of DES year 1 data. These are the deep fields, DES deep fields there, and then the 2 LSST bands, with the final one being this line here for the year 10 kind of fiducial sample that they talk about.
P here means what?
Sorry,
The y-axis there.
this is the probability that a galaxy, if I selected it, would be at this redshift, and it integrates to 1. Right. And so
Is that also true for the lensing?
the lensing kernel, it's the probability.
Multiply by what number to get it to be a probability? Or of actually being lensed?
So it's actually not technically the probability that it's lensed, but it's the contribution to kappa from the integral. So it's not exactly a probability, but it's roughly that, right? And then this shows you kind of quasars, for example. So the relative numbers here, the relative amplitudes just have to do with how narrow things are, right? Because they have to integrate. So there are way fewer quasars, for example, than there are LSST galaxies. That's not the point I'm trying to make with this plot. What I'm trying to get is the redshift kind of scaling. So these are the quasars. Quasars kind of typically peak around a redshift 2 to 3, and then they fall off a cliff pretty quickly. And then these show you the dropouts, right? All the way out to R dropouts, which you can see are peaked around a redshift of about 5. So R dropouts redshift 5, G dropouts roughly redshift 4, U dropouts approximately redshift 3, and then these two B dropouts are roughly a redshift of 2, right? So the interesting thing here, oh yeah?
I don't know if you already covered these redshifts, but there's also this point about when you go to redshifts 5 and 5.5, etc., you get a drop bluebirds of the Lyman alpha rather than the Lyman break. And so the Lyman break thing is like washed out.
Yeah, so pushing to here gets really hard. Right. So if you...
Even redshift 5, it's still okay.
Yeah, so that's why this cuts off here, right? So we've tried to stay away from all that fascinating science that we know happens here. Right? Don't do anything fascinating. It's always a bad idea. But the interesting thing about this, right, is just looking at the red curve and the green curve and the blue curve compared to the big shaded orange, purpley thing, I can tomographically decompose this lensing kernel across essentially whatever that number is, 80 or something % of the observable volume of the universe, right? And I can do this with extremely well understood samples of objects. No. So, my claim is that the combination of this new generation of deep imaging surveys and the new generation of CMB gives me the possibility of cross-correlating those two different data sets to do all of these things that I mentioned earlier we want to try and do. And cross-correlation is a good way to write papers, but it's really only interesting if the combination actually gives you more than the sum of its parts, right? And I'm arguing that in this case, I'm going to use the optical survey to isolate the piece of kappa that I want from narrow redshift slices, narrow meaning of order delta z of a half or so, simultaneously with increasing the signal to noise and downweighting the systematics that are in the lensing map. What the lensing is giving me is sensitivity to both of the metric potentials and directly measurements of the matter, right? So the combination of the two is each kind of building on their strengths. So this shows you some work I'm doing with a graduate student at Berkeley and Simona Ferraro, who's now at LBL, which shows you kind of the rough signal to noise that we have on these kind of observations now. These are galaxies selected from the WISE or UNWISE catalog, crossed with Planck CMB lensing. So this shows you the galaxy autocorrelation power spectrum as a function of angular multipole. And then this shows you the cross correlation of sample 1 with the CMB lensing, sample 2 with the CMB lensing, and sample 3 with the CMB lensing. And these are at, roughly speaking, redshift 1/2, 1, and 1.5. And this covers 20,000 square degrees. And you can see if you count this up that these are signal to noises of about 50 or 60 in each redshift slice, right? So we're talking about tens per redshift slice in redshift slices that are of order delta z of a half or 1-ish. And that is the current state-of-the-art signal to noise. This shows you the signal to noise that we would get in the future if I had LSST and CMB stage 4. So this shows you as a function of the number of galaxies per square degree. Remember, it was pretty easy to get to 10 to the 3 or 10 to the 4 galaxies per square degree from those luminosity function fits I showed you before. And then this shows you the signal to noise you would have in the cross correlation at redshift 3, the signal to noise you'd have in the cross correlation at redshift 4. We also have figures for redshift 2 and 5. I just didn't bother to put them on the plot because you can't read anything. But you can see these are numbers of hundreds. This is scaled to f sky of 1. So if you think that we cover half the sky, then you multiply these guys by 1 on root 2, but still very, very large numbers. And this shows what happens if you just do the raw signal to noise. And this shows you what happens if you do a little bit of cleaning with lower Z tracers, which can boost this up by some non-trivial factor in the case of CMBS4. So the point is that we can achieve hundreds of sigma per redshift bin in multiple redshift bins. I've shown you 2, but I can also do this at redshift, at other redshifts as well, right? So what I can do now, kind of in one broad bin at redshift 0 to infinity, I will eventually be able to do with these new instruments in multiple bins all the way from redshift 2 up to redshift 6 with signal to noises that start getting interesting, right? Hundreds and hundreds in this case. I'll skip through this. This is just some fiducial samples. So this just shows you how things kind of break up. So these are what are known as BX galaxies. All of these designations are kind of a little bit obscure. They're kind of optical astronomer naming conventions. But these are dropout galaxies at redshift 2, right? So this shows you the galaxy autocorrelation function, just the angular correlation function of those galaxies in this redshift, roughly delta z of 0.5 around redshift 2. This shows you the power spectrum of the lensing measured, for example, from CMBS4 or something like that. And then this shows you the cross correlation between the galaxies and the CMB, and it's quite low because only a small fraction of those galaxies, of course, only a small fraction of the CMB lensing kernel is probed by those galaxies, right? I've also got structure in the foreground and the background. The line across here is the shot noise that you would get if you went to 25.5 magnitude, which is something we forecast you could fairly easily do with something like LSST. So you can see that your signal to noise limited all the way out to L's of just over 1,000. This is the noise per L, which is actually a little bit misleading when you're plotting things with L's of thousands here. And so we've also broken it up into bins and shown you the 1 sigma error that you would get on a bin if you averaged over that many L's per bin. These show you the noise curves that you would get using kind of current generation instrumentation, things that's being built right now, and then eventually CMBS4, which you'd see would be delivered signal to noise greater than 1 all the way out here to high L. And again, these error bars show you what happens if you bin up the noise per L into actual errors in bands. And given these two sets of error bars, you can predict the error bar on the cross correlation, and so I've just shown that also in the bands. This colored band off here to the right is our forecast of where we think we can no longer model this, just due to things like nonlinear bias, decorrelation, all of those other kinds of issues, where even if I could try and model this in simulations, there's so many parameters involved in modeling that physics that you don't gain much. Obviously, this is a little bit of a fuzzy boundary, but it's somewhere around L of just a little bit over 1,000. And so you can see here that you're basically theory limited for these kind of measurements, more than you are observation limited. This shows you the same thing at redshift 3. Again, almost out to the theory limit, you're pretty much signal to noise limited, and with CMBS4, the same thing, almost out to the theory limit. Things get better and better, of course, as you go to high redshift. The theory limit is moving to higher and higher L, so smaller and smaller scales, because everything is getting further away, and of course the structure is getting much more linear. And so again, notice we have these extremely tiny error bars, even out here at redshift 4, and you can keep going this all the way out to redshift 5. And beyond this, as Hamza mentioned, the things get hard to model when you start going up here. Notice these are getting pretty deep now. I'm talking about a Z-band depth of almost 26th magnitude. But it turns out if you just read the LSST specs, they claim they can do that. So right in principle, this is something we can do. So let me walk you through an example then of what you could do with this. One of the goals of observational cosmology is to try and measure the evolution of the matter power spectrum with time, right? So I want to measure the autocorrelation of the matter as a function of scale and redshift. And here's a schematic way you could do that. We'll talk about how you really do it in a second. But I can, through the powers of higher algebra, measure PMM by multiplying PMM by B, squaring it, and dividing it by B squared PMM. So I think everyone's good with this first step, right? So if I say that B times P matter is the same thing as the cross correlation between matter and halos, and 2 powers of B gives me the autocorrelation, then this is roughly the cross correlation of matter with halos squared divided by the halo power spectrum. And then these power spectra are what are basically being projected to give me these angular power spectra. So roughly speaking, right, I'm making liberal use of a twiddle here. This is roughly the kappa galaxy, right? So kappa probing the matter, galaxies probing the halos, and the galaxy-galaxy power spectra, right? So roughly speaking, if I had access to kappa G and GG, something I do with twiddles could give me back the matter power spectrum, right? Now, clearly this is not what we actually do, although sometimes I do wonder about my colleagues. What you would really do, right, is you perform a joint fit to the combined data set. So I have some model for the cross power spectrum, the auto power spectrum. It has a bunch of nuisance parameters, but it also has the thing I want, which is this matter power spectrum, right? And so we would fit that model. Now, if I only had the galaxy auto spectrum, then there's a huge degeneracy between the amplitude of PMM and the unknown B, right? In fact, in the way I've written it here, it's a perfect degeneracy, and so it couldn't be broken. But the minute I have both of these, you notice they depend on PMM and B differently, and so jointly fitting breaks that degeneracy, and I can measure both independently, right? So that's basically the idea. So I'm going to try and use this to measure the amplitude of this power spectrum, sigma 8, and the bias simultaneously, right? That's the goal. Now, pretty obviously, just from this way of writing it, what that means is I need a model for the auto and the cross power spectra of bias traces, all right? Now, almost goes without saying that every time you improve the data, you have to go around and improve the theoretical modeling if you actually want to get to the science result you want at the end. And so the question we've been asking ourselves for the last several years is that if we're going to have all of these great data, what's the right theoretical framework for analyzing the data? And just to remind you, I need a model for the auto and the cross spectra of bias traces that works on these kind of large to intermediate scales. Unfortunately, even though we're at high redshift and even though I'm saying large scale here, linear theory just isn't good enough. You need to include nonlinear corrections, and something that people often forget is that the minute you start including nonlinear corrections, you need to worry about bias and scale dependence of bias and things like that. So there's a whole host of evils come in once life goes nonlinear. And just to remind you, these are highly biased objects. So you can go into the literature and actually measure the bias of these objects. Here it is as a function of magnitude and of redshift. And you can see that the biases, certainly at high redshift, are approaching 5 to 10. Right? These are extremely biased objects. Even though they're living in sort of 10 to the 12-ish solar mass halos, 10 to the 12 solar mass halos are rare and biased at high redshift. So these guys are pretty. So this is good in terms of signal, but it's bad for the following reason. This just shows you modeling and n-body simulations, the work I did with Mike Wilson, based on current and old data, actually, of redshift 3 and redshift 4. This is just the angular correlation function. These points show you the data, and then the green and blue lines just show you some n-body populated model, which basically matches the number density, the redshift distribution, and the clustering of these objects. And then in the simulation, I can go in and I can also have access, of course, to the matter. And so I can say, what is the bias actually for these objects? And so this is shown here for redshift 3 and 4. Redshift 4 is the higher bias. And it's shown for measuring the galaxy auto bias and the galaxy matter sort of cross bias, right? There's two things to notice. One is notice that this is an extremely scale-dependent function, right? And the other is that the auto bias and the cross bias don't match. Everything's great at large scales, right? At large scales, the bias is constant, and B is B, and everything's good. But on these scales, that is no longer true, right? Now, this is in configuration space. It's perhaps slightly easier to see this if I look in power spectrum space. So this again shows you the power spectrum versus K. This shows you linear theory here, and then the nonlinear theory is this kind of dashed line. This is from the n-body simulation. This shows you the galaxy matter cross correlation. And then this shows you the autocorrelation. And then what I've done for these two lines is I've taken this, whatever that is, orangey line and this gray line, and multiplied them by the appropriate powers of B, right, to have them all match, right? So if B was just B and it was a constant, then these things would all be exactly the same. And what you can see is that nonlinearity sets in here around, I don't know, K of 0.2 or 0.3-ish. But notice that the scale dependence of the bias is setting in at K of 0.1, right? Roughly speaking, the same scale as nonlinearity, but actually worse in this case. And notice that it's quite different for the auto and the cross spectrum, right? And this just shows you the same thing at redshift 4, right, where it's even worse, actually. So if you ask, how do people currently model these data? Well, the standard model is you use this so-called halo fit fitting function for the matter power spectrum, which is just some fitting function that's auto-magically computed for you when you run the standard Boltzmann codes, right? So it just drops out. It's amazing. And most analysts assume a scale-independent bias, which I've been arguing is not a very good idea. And they tend to assume that bias is bias is bias. So one extension that's motivated by Peake's theory is to use this so-called quadratic bias, which goes under the name of B10 and B11 for reasons I will spare you. We found in fitting to simulated data that we need to augment this with a linear term. So if this is a 0 and this is a 1, it's kind of obvious that there has to be a half. This is a non-analytic function, right? So this cannot arise by any actual theory, but it really does make the fits way better, so we put it in. And so our model, in quotes, right, for the matter halo cross correlation is B times P halo fit, or B squared times P halo fit. And I'm allowing these to all be free functions, which I'm just going to fit, right? So remember, the standard model is these two constants. We've extended the standard model with a, no, I can't possibly justify it, but it helps, and something we can justify, which turns out to not help very much, times P halo fit, right?
So, can you explain to the ignoramuses why you can't have a K term?
So this is a 3-vector, right? So K is the square root of K squared, and I can't get a square root by any standard, it's a non-analytic function at K to 0.
So you're just assuming at the beginning that it's an analytic function, and apparently you're saying
I mean, it will be an analytic, whatever bias is, it's some analytic function that I must be able to write down, right?
So then why are you introducing this K?
Because it helps the fit.
Yeah, I understand that.
Right, but I can't justify it at all, right? So what this is saying is that this model is clearly broken. And this is an example of that. So no, there is no way I can justify this. But empirically it helps. Right?
It also breaks the reflection.
It's a horrible thing. Let's not keep ragging on it. We don't like it. But the other thing, notice, is that, right? So I've given it in red so that I've totally stolen my own punchline. But most people at this point would be completely happy with this. But notice that it assumes that the bias is bias, right? If you don't subscript anything, then that's the literal statement that B equals B, right? So that's the standard approach. Our approach is to use perturbation theory. And the cool thing about this, right, is that we all love CMB primary anisotropies because the theory is beautiful and clean. All we're going to do is basically take that same theory but go to higher order, right? And so it's still beautiful and clean. And if you're a theorist, it's absolutely wonderful because it turns out the formalism involved in CMB lensing is essentially ripped off from or independently derived, I don't know, from perturbation theory. So you actually end up doing many, many of the same calculations. It's really quite pretty. So the cool thing, something that's happened, right, is that surveys get larger. More of the modes we measure well are now quasi-linear, right? So linear perturbation theory is not enough, but I need to do a good job of measuring something that's almost linear. And this is fantastic because over the last several decades, perturbation theory has developed steadily by borrowing, stealing ideas from other fields. And so the fact that this is also the direction that the experiments are pushing us is just highly fortuitous. And at Berkeley, we've been developing a lot of these analytic models for things like BAO and redshift-based distortion analysis, but it just drops straight across into this setting. So, in this framework, you have some model for example, the matter-galaxy cross-correlation, which will have some kind of tree-level terms, some terms that are one loop, and then a bunch of terms depending on the bias. I'm not going to write out what these are, but they're all completely calculable with just standard techniques. And so you have this set of parameters that you would fit to a bunch of functions which are all basically pre-computed. And then you can just ask how well do they do. So again, here's a comparison to n-body. Here's at redshift 2. This shows you the halo power spectrum, the matter power spectrum, and the cross spectrum. And then this just shows you how well linear theory does, right? That's these blue lines assuming a constant bias. Perturbation theory is the red lines, which you can see actually do really quite well even at redshift 2. And then for halo fit here for these green lines, halo fit is a fit to this curve, so it does pretty well for the curve. And then here I'm just showing you how bad a constant bias is, right? Just so I don't have to fit too many parameters. And you can fix one of these guys by multiplying by that, b plus k squared type of thing, but you can't fix both of them simultaneously. So I didn't plot that, but it turns out to be true. This just shows you it at redshifts 1, 2, 3, 4. You can keep doing this. It more or less works. So this is what happens if you go and fit those two kinds of models. So this is the true value of sigma 8 in a simulation. This is the likelihood that you get out of those data if I fit with perturbation theory. This is the likelihood you get out if you fit with halo fit, assuming the flexible b plus k squared model, but that the two biases are the same. This is at redshift 3. I can show you the same plots at redshift 1 and 4 and everything else. It looks basically the same. Perturbation theory works. This gets tighter errors. It's up to you which one you prefer, right? Clearly, this is a big mistake. Almost all of this comes from the assumption of this biases being equal thing, right? So this just shows you the actual residuals here at redshift 2 and 3. I mean, I'm sorry, I've kind of skipped redshifts all over the place. But what you can see is that, out to L's of 2000 or something, the green lines, which are these perturbation theory models, are basically just fitting at all redshifts. This little wiggly thing here is actually noise in the n-body simulation, because you can see we're way sub% at this point. So you're just picking up numerical noise. And the fit, such as it is, in these more parameterized, models, you can see it's trying to struggling to pass through the points, and so it's coming to some consensus. And so what you find actually if you fit the chi-square is it's terrible, and your results are really unstable depending on where you cut. So the only way to get an unbiased result is actually to cut all the way back here to L of 500, which throws away essentially all of your data. Right? Yeah.
Did you also test on newer versions of halo fit, like the simulators?
We tried a bunch of different things, yeah. So I think, I say this here. So part of this issue is exactly what you said, that PMM is not actually right from halo fit. It's off by between 5 and 15%. Turns out for the model we ran, it's actually pretty damn good, as you saw earlier, because we ran something very close to where it was trained, just because if you're going to pick a cosmology. But a lot of it is really just this B of k assumption, right? And then this assumption here, which is just not true. And you can completely calculate this and just show it's just not true. So at high Z, modeling the bias, I claim, is at least as important as modeling nonlinear structure formation. And there's a way of thinking about this as a field theorist that makes perfect sense. If I think about this sort of effective field theory language, the nonlinear scale is shifting to higher and higher k as I go to higher and higher redshift, right? But the scale associated with halo formation is basically the Lagrangian radius of a halo. So if I'm looking at a fixed mass, that's a constant. So there's just a natural point where at some point you worry about this more than you worry about that. Which of these k's is smaller? I'm doing 2 expansions. Which one matters the most? And by the time you're at redshift 2, for anything bright enough that I can really be doing a good job of measuring it, the answer is this one. All right, that's just it.
Not being able to VMH, is that the same as saying that there's stochasticity?
It's decorrelation of the field. R is less than 1. Right.
So the thing that is an R which is about 1.
That's right. Exactly. Exactly. OK. I'm going to skip over this, but it turns out there's a lot. Everyone who does the analysis of CMB lensing always works in Fourier space, and I completely understand that. There's an awful lot to be said for working in configuration space just because of the way in which R departs from 1. In configuration space, it's 1, and then it completely breaks. In Fourier space, it's 1, and then it slowly degrades. So depending on how good your model is, that can be a problem. All right, I'm almost out of time, so let me just quickly, just straightforwardly skip to the conclusions here. I've tried to argue that we're about to cross a threshold where the quality of the data is just going to really jump, both in the CMB and in the optical. Right? We're talking huge advances. And the combination of both of these things happening at the same time is actually way more interesting than either of them happening in and of itself. As always, better data requires better modeling, where by better I mean mine. With primary anisotropies, linear theory is 99.999% of the story. But at lower redshifts, that's just not the case. We need to model both the nonlinear matter clustering and the bias, right? Because we're dealing with bias traces. Just on a personal note, one thing that I find kind of interesting is that, back in the day when Dick Bond and others were inventing the fields of CMB and LSS, it was the same group of people, so the fields were the same, right? And they used the same language and they ran the same codes and life was grand. But naturally, of course, as fields mature and they specialize and they become more involved, these two fields have grown apart a lot, right? So if you go to CMB conferences now and large-scale structure conferences, people are speaking a completely different language. They're worried about very different problems. On the other hand, I think scientifically we're witnessing a recoupling. There's reasons for these fields to get back together again. And that's also interesting, just as a personal note for me, is that these both represent teams of very smart people who've come up with very interesting solutions to problems that are often the ones that the other side hasn't got to yet. So by the simple process of stealing their papers, crossing out their names, and writing your own in crayon, right, you can actually make breakthroughs in kind of both of these fields just by having read articles in both. And I think that's kind of an interesting thing. I've tried to argue that by going to high redshift and working on these sort of large scales, meaning CMB accessible scales, this is a really attractive problem for a theorist because you can work analytically, you can talk about error bounds, you can feel like you're actually doing some physics calculation. And I've really focused here on this particular science case, but obviously this works for anything that you're doing at high redshift. And in particular, it's quite interesting for sort of line intensity mapping surveys. 21 centimeter being kind of the prototype. And I think the stuff we've been doing works in both real and redshift space. And so you can just basically take this whole formalism across and just apply it directly to line intensity mapping. And as far as we can tell, at least with our preliminary investigations, it just works out of the box. So that's really, really cool. All right, thank you.
We have time for some questions.
So you just said it works pretty much out of the box for the line intensity mapping case. I guess the big advantage it would seem there for a lot of cases of the intensity mapping over the PhotoZ surveys is you have really high redshift resolution.
That's right.
The lensing kernel is really smooth, so is that something that...
So, it's not obviously clear that the prime science case for line intensity mapping would be, say, to cross-correlate with CMB lensing. Because, you could imagine coming up with a scheme to do it. I mean, Whaley's imagined coming up with schemes to do this, but it's just hard to do, whereas this is easy to do. And it's like, they're going to do it. Why would you focus? But just to, to give an example, I don't know if we have, I don't know what things I put in here. So we have these simulations that we've been running to do intensity mapping science. So here's just an example of a plot, but if, I'll just see if I can. So again, right, you notice you get a very scale-dependent bias, right, even in 21 centimeter. Somewhere in here, yeah, this shows you an example. So this shows you the monopole and quadrupole in redshift space, and this is the tree-level result, this blue line, right? So this is not even including the one-loop terms, which we totally know how to include, right? And you can see that it's basically dead on. Here, the simulation just becomes noisy even in a gigaparsec, unfortunately. But you know, it's clearly roughly working. You know, this is n body divided by theory, right? So 1 is working. And we also looked at L equals 4, but the simulation's like this, but yeah, it does kind of go around 1. And so here's at redshift 2, and of course things just keep getting better as you go to redshift 6, right? So this is tree level. I have a student who's actually working on doing the one loop calculation. The interesting question there is how you include redshift space distortions at one loop, and we have a really clever way of doing that, which hopefully works. It's clever, I don't know if it works. But yeah, you can just totally use it for line intensity mapping. Yeah.
Any more questions? I had a question. Are you planning on putting any Dropout stuff into the decadal survey as a concrete project proposal, or?
We have a bunch of you know, we've got some science white papers already gone in. We have a bunch of project and technology development, technology readiness. They've got some name for it, which are drafted, and hopefully we'll make it. But yeah, that is the intention. It's hard to get people motivated to write white papers, unfortunately. And there's a small number of us beating this drum. But yeah, fingers crossed. I think, you know, the other thing, you know, I didn't talk about this, but you know, one of the nicest samples you can have is these U-band dropouts. U-band dropouts are these objects at redshift 3. They have almost no interlopers. But LSST, it's hard to get U-band imaging actually, right? LSST doesn't go very deep in U. It goes very deep, but it doesn't go really deep in U. So you're actually entirely limited by the U-band depth. If you could increase it just a little bit, it turns out you're brighter than M star in the luminosity function. So the gains are exponential with depth, right? So we've talked a lot to the LSST folks who are doing all the scheduling. Our original plan was to steal from Y and Z and put it into U, because you know, who cares about Y and Z? But it turns out that doesn't work because of the way they schedule things. So you'd have to steal from G and R. That's going to impact their science case way more. But I think one thing you could imagine, right, is, you know, if you took CFH, which has a spectacular U-band imager, and just said for the next 5 years it's just going to do U-band imaging over some large fraction of you know, the field that hasn't been done by, you know, clouds or whatever, the gains are exponentially good. And that sample, it's right at the peak of the CMB lensing kernel, and it has almost no interloper contamination. It's just really hard to image in U, right? So I think there's things you could do for sure that would make this better. And we have, Mike Wilson dumped this paper. It has 250 references, and it's 60-something pages on this science case, trying to make it more real. I mean, we've actually run these things through exposure time calculators and schedulers, and you know, this is a little more than a straw man. But there's a long list of 2.5 pages of things we didn't have time to do in our 60-page, 250 reference behemoth, right? There's a ton of work that needs to be done to turn this crazy idea into something that would actually work before someone, you know, on an LSST scheduling tack is going to take this seriously. Yeah.
Since you're doing a lot of detective modeling in Lagrangian space, and
yep.
all the data lives in Eulerian space, whether you want to or not.
Yep.
If you actually really measure these halo, these bias terms and these specificity terms in Lagrangian space, are they fundamentally differently behaved?
A little bit. The shear terms are. The shear term that you measure in Eulerian space, the bias B sub s squared, is largely generated, well, is at least a reasonable fraction of that is generated by evolution, and thus is much smaller as a term in Lagrangian space. The main reason we've been working in Lagrangian space is because of the BAO and RSD science. It's much easier to handle RSD. Much easier to handle RSD in Lagrangian perturbation theory. It's a little harder to handle higher order functions, it turns out. So the 3-point function stuff we've been looking at, we've kind of vaguely backed back to Eulerian theory.
Why aren't things always easier in Lagrangian? I mean, naively, I would have thought things are always easier in Lagrangian space.
It's hard. Well, maybe you're just cleverer than we are.
If you don't know about data, unless you're only doing memory simulations where you can equally do it in Lagrangian space, aren't you always better?
It's hard to organize the calculation of the 3-point function we found. It's very hard to organize. Too many angles. Get it in redshift space. People keep calculating the 3-point function in real space, which is an utter waste of time, right? Well, it's not an utter waste of time, but it's not. That's the easy part. There's way too many angles when you have multiple lines of sight and multiple vectors. It's really hard to do.
Sorry, it's the same number when they're in space.
Well, only because they don't include redshift space distortions. Yeah. So, but yeah, you know, we have this new scheme which we also think includes redshift space distortions very naturally. And one of the things it does really nicely is it includes the bias dependence of the redshift space distortions. So one of the hard things to do in redshift space distortions is the mean infall velocity, which is bias tracer dependent, right? Because the higher the bias, the more massive the halos you're sitting in, and so the larger that term is. Almost everyone is including that term unresummed, and that tends to be one of the major reasons why these things don't work very well. We have a scheme now that works for an arbitrary endpoint function that just routinely resums those. We think it's going to be a big deal, but we haven't demonstrated that by comparing it with simulations and stuff. But all of the tests we've done theoretically look great. I have one graduate student working on that, but you know, one graduate student is a slow way to make progress.
On that note, maybe let's thank Martin again for our next talk.